All right, I want to do 3 more examples here in this last part. So we're on example 4. So let's try this one. This is the integral of the square root x natural log x dx. Again, our key here for doing integration by parts is 2 things. First off, we have 2 functions that are multiplied together. That's kind of a big indicator to do integration by parts, but also this natural log. Pretty much anytime you have a natural log, you're going to be doing integration by parts. So we need to set up a u, and we need to set up a dv. Now we have to be careful here. We want to set up our u into something that we can take the derivative of and something that breaks down. We want to set up our dv into something that we at least know how to do the antiderivative of. A big clue is that anytime there's a natural x, almost always make that natural log x be the u. Because when you take the derivative of that natural log, you just get the 1 over x. So we're going to let the dv be what's left, the square root x dx. If you had gotten these wrong and you tried it out, you would get to a point that you would just be stuck and you wouldn't be able to go any further. If you get stuck on integration by parts, start back at the beginning and try switching up your u and your dv to see if it works out. All right, now that we have the u, we need to find du, which is just the derivative of the natural log, so 1 over x dx, and then the antiderivative of dv. This is actually x to the 1/2, so the antiderivative is going to be taking that x to the 1/2, raising that up to be x to the 3/2, but then dividing by 3/2, which is multiplying by 2/3. So that's going to be our v. Okay, that means that my integral here is now going to be u times v, so 2/3 x to the 3/2 natural log x, minus the integral of v du, 2/3 x to the 3/2 times 1 over x dx. Simplifying that down and doing the antiderivative. Copying down this first term. We can multiply these x's together, so we still have that 2/3. X to the 3/2 divided by x to the 1 is going to simplify that down to be x to the 1/2. It's just a quotient rule thing for exponents. Okay? And then finally, we're just going to do the antiderivative there inside that integral. So copying the first term. Same antiderivative, this is x to the 1/2. We're going to raise that up to 3/2 and divide by 3/2. So we're going to be multiplying by another 2/3 out in front. 2/3 times 2/3 is 4/9. And then this is x to the 3/2. Don't forget your plus c. Cool, and that's it. So that's going to be our antiderivative for square root x natural log x. All right. Now let's get into the really complicated ones. And this is actually pretty important. You're going to see this a lot. I teach the Calc 3 and the differential equations class as well. And this next example has come up in both of those classes. So it is important. But it's weird and maybe not something that you guys have ever seen before. So let's look at this. The integral of e to the x cosine x. This is going to be integration by parts, so we're going to set up our u and our dv. It really does not matter which one you let the u and which one you let to be the dv, because if you keep taking the derivative of e to the x, it just stays e to the x. If you take the derivative of cosine, it's just going to bounce back and forth between cosines and sines. So neither one of these functions, when you take the derivative of, does it really start disappearing. So we're going to have to do a little trick here. For me, I'm going to let u be the e to the x, and the dv I'm going to let be the cosine x dx, just because that's the order that it is in my integral here. Once you have the u and the dv, you have to find the du and the v. The derivative of u is just going to stay e to the x, but I'm going to throw the differential dx on there. dv, which is cosine x dx, the antiderivative of cosine x dx is just sine x. Okay, so now just copying what we have. We have our initial thing we're trying to find, the integral e to the x cosine x dx. So we're going to set that equal to u times v, which is going to be e to the x sine x, minus the integral of v du. I'm going to write that as e to the x sine x dx. All right, and we're kind of in the same boat again, where we have, again, an integral with two things multiplied together, and there's not really any other way to do that but another integration by parts. So let's just try another integration by parts and just see what happens. So for this integral here, again, I'm going to let u be the e to the x, dv I'm going to let be the sine x dx. Then du is still e to the x, but with the differential dx. The antiderivative of sine x, got to be a little bit careful here because it's actually negative cosine x. Okay, now, again, starting back over from the beginning of the line here, we have the integral of e to the x cosine x dx is equal to, just bringing this down, e to the x sine x. We have the minus integral, and then this integral is what we're going to substitute into an integration by parts. So that negative sign here is going to have to distribute into the integration by parts for this e to the x sine x. So let's go ahead and write that out. That's going to be the u times v, which is negative, so I'll write that as negative e to the x cosine x, minus the integral of v du. I'm going to write that as negative e to the x cosine x dx. All right, I have a ton of negative signs here, which I don't really like, so I'm going to fix that. Copying down this, I have an e to the x sine x. Distributing this minus sign, I have a double negative, so plus e to the x cosine x. I actually have a triple negative here, so this negative onto these two negatives is going to be negative the integral of e to the x cosine x dx. All right, and now we're back where we started. I wanted to find the antiderivative of e to the x cosine x dx, and on the right hand side I ended up with another integral e to the x cosine x dx. What I'm going to do now is I'm actually going to add this entire integral back to the beginning. So if I just add this onto both sides of my equation here, I'm going to end up on the left hand side with two of these integrals e to the x cosine x is equal to e to the x sine x plus e to the x cosine x. Then, if I want to solve for the antiderivative of e to the x cosine x, I'm just going to divide by 2. So the integral of the x cosine x dx is going to be 1/2 times e to the x sine x plus e to the x cosine x. Don't forget your plus c. Okay, so a technique that maybe you haven't seen before, but we had to do integration by parts twice. And not only do we have to do that, but we actually ended up with a formal definition for an integral that has the same integral on the right-hand side of the equation. So we just wrapped this back around to the front like a snake eating its own tail and added this back to the initial thing that we had all equal to. Then we just needed to get the coefficient off, and we just divided the coefficient over to the right-hand side. I promise you, if you take the derivative of this right-hand side, it will simplify down to be e to the x cosine x. Okay, great. I have one more example that I want to do. This isn't a hard example. It's just not something that we've seen yet. I forget which example we're on now. 6, 7, 8, whichever one it is. I'll do this one quick. So what we have not looked at yet is we have not looked at integration by parts for definite integrals. So far we've only done indefinite integrals that did not have the limits. So if you do have limits, it's okay, just do the same thing. So we're going to have a u and a dv. We're going to let u be the x this time. dv is going to be the e to the negative x dx. I'm writing it out like that because I know when I take the derivative of the u, it's going to simplify down. Derivative of x is just 1 dx. Be careful here. Antiderivative of e to the negative x is we're going to divide down that negative 1 and then just leave the e to the negative x alone. Okay? This is now going to be equal to the integration by parts, u times v, which is negative x e to the negative x, minus the integral of v du, which is negative e to the negative x dx. The limits from the first equation move down. So this is also going to have the same limits from 0 to 4. But not only does this integral have the limits, but this first half of the antiderivative also needs to be evaluated from 0 to 4. It's up to you when you want to do that. You could go ahead and do this now, plug the 4 in minus plugging the 0 in, or you could wait to the end. I usually wait to the end. So I'm just going to copy down this first term. Distributing the negative signs is going to make this a positive, but then the antiderivative of e to the negative x is negative e to the negative x. This would also need to be evaluated from 0 to 4. Whenever you have two things that are being evaluated between the same limits, what you can do is you can combine them together and then just evaluate the whole thing from 0 to 4. This is what I usually do for these. I usually just go ahead and find the antiderivative using integration by parts, and then at the very end plug in the limits. So if I plug 4 into this, I'm going to get negative 4 e to the negative 4 minus e to the negative 4. That's going to be minus plugging 0 into this. This first term is just going to be 0 minus, if I have 0 into this one, I get e to the 0, which is 1. Combining like terms together, I have negative 5 e to the negative 4 from these two, and then a plus 1 because the two negatives canceled out there. Okay, great. But that is integration by parts.